Good morning, class.
Good morning.
So, how are you today? Do you remember our lecture last time?
Yes, it is.
Joseph, do you remember what was our topic last time?
Our topic last time is all about Pythagorean theorem.
Yes, last time we discussed the Pythagorean theorem. We discussed the geometric aspects of the Pythagorean theorem, and we also talked about the influence of a Pythagorean theorem on human civilization. So the Pythagorean theorem was really motivated by very practical considerations. But we can look at the Pythagorean theorem purely mathematically. It's just an equation having some solutions. So today I will talk about Diophantine equations, of which the Pythagorean theorem is one example. It's probably the most famous example. And I will show you the outline of my talk. So at first let's go back to the notion of the greatest common divisor of two integers. Do you remember what we mean by a greatest common divisor? Danica. Greatest common divisor or greatest common factor, the GCF. Sometimes it's called the GCF, sometimes it's called the GCD. For example, if we have two numbers, 10 and 21, what is the greatest common divisor of 10 and 21? 1. What is the greatest common divisor of 30 and 18? 6. So what are the factors? What are the factors or divisors of 18?
1, 2, 3, 6.
1, 2, 3, 6. No? So if we look at 18, 1, 2, 3, 6, 9, 18. No? 1 times 18, 2 times 9, 3 times 6. How about 21? This is 1, 3, 7, 21. No? So the common factors, what are the common factors of 18 and 21? We have 1 and 1. We have 3 and 3. So the greatest common factor or the greatest common divisor is just the greatest among all the common divisors. So we write GCD of 18 and 21 is equal to 3. Do you remember in grade school, how do we compute the GCD of two numbers? By listing, yes. How do we compute the GCD? For example, what is the GCD of 56 and let's say 27? So we list down all the factors of 56, and this is 1, 2, 4, 7, 8, 14, 28, 56. How about 27? We have 1, 3, 9, 27. Again, the GCD in this case, in fact, there is only one common divisor, and that is the number 1. So the GCD of 56 and 27 is 1. Do you know what we call those pairs of numbers having GCD equal to 1? We say that they are relatively prime. It means that those two numbers do not share a factor except 1. Of course, all numbers are divisible by 1. So 1 is always a common factor. But whenever there's no other common factor other than 1, then we say that those two integers are relatively prime. So I'll just write down the word, relatively prime. So 56 and 27 are relatively prime. However, 18 and 21 are not relatively prime. Now, this is what we call the naive way of computing the GCD. Because it is very natural. We just list all the common divisors. Now, it becomes a problem when your numbers are very big. When your numbers are very big, then you have to guess what the factors are. And the bigger the numbers are, the more difficult it is to compute the factors. So we need a very special technique in getting the GCD. And this technique was provided by the Greeks. It is called the Euclidean algorithm. And I will teach you the Euclidean algorithm. Again, the concept of GCD is very important for the study of numbers and their equations. This is why I am beginning this lesson by talking about the GCD. So when we divide two numbers, let's say, let's divide 35, let's divide it by, let's say, 6. What do we do? 35, how many 6s are in 35?
5.
There are 5 6s. So 6 times 5 plus plus 5. This is what we call the quotient. And this is what we call this is the remainder. This is what we call the remainder. Let's do another division. Let's say 72. Let's divide 72 by 5. 5 times, how many 5s can we find in 72? This is 14. 2 is the remainder. So this is the quotient. 14 is the quotient and 2 is the remainder. How about 72 divided by 6?
That's 12.
72, 6 times 12 plus 0. Whenever the remainder is 0, it means that 72 is a multiple of 6. Another way of saying that, 6 is a factor of 72, or 6 is a divisor of 72. So whenever the remainder is 0, then you have a complete division. Okay? Now, this way of writing a number in terms of its divisor, its quotient, and remainder is very important. I shall now discuss how we can efficiently compute the GCD of any two numbers. Now, let us compute the GCD of 56 and 27 without getting all the factors. Okay? So, we want the GCD of 56 and 27. This is how we do it. We divide the bigger number by the smaller number. Okay? 56 divided by 27. We should get a quotient and a remainder.
That's 2. Remainder
2, remainder 2. Okay? Now we repeat it, but this time the divisor will become our dividend. I shall bring this down. This is 27. And then the remainder I will bring down as a divisor. So this is 2 times 13 plus 1. Okay? Now I repeat it. We will keep on repeating this process until we get a remainder that is equal to 0. So 2, right? And then the remainder we use as a divisor. 1 times 2 is equal to 0. then the process stops. The GCD is always the last non-zero remainder. The GCD is the last non-zero remainder. In other words, the GCD is 1. Okay. This process of getting the GCD is called the Euclidean algorithm. It was introduced by Euclid, and it is very efficient because we do not have to compute the factors of two numbers. Also, it is probably the algorithm or the method that is being used in a lot of computer programs whenever the GCD needs to be computed. Okay? Let's look at another example. Now let us use the Euclidean algorithm to get the GCD of 234 and 56. Can I call on one of you? Jennifer, you'd like to try? So first step, we divide the bigger number by the smaller number. 234 is equal to 56 times a quotient. That was fast. 56 times 4 is 56 times 4 is 224, so the remainder is 10. Now you bring down the divisor 56 and divide that by the previous remainder, plus 6. And then we repeat. 10 is equal to 6.
4 is 6
Six.
is equal to 4 times 1 plus 2.
Plus 2.
4 is equal to 2 times 2 plus 0.
Okay. So now we have reached a remainder equal to 0, which means again that the GCD is the last non-zero remainder. So the GCD of 56, that is 234 plus 56 is equal to 2. So this is the Euclidean algorithm. So if you have really big numbers, there's no need to get the factors because that is very difficult. But we can perform division. We can do that by hand. And the process stops in a few steps. Okay? Now, I want to talk about linear Diophantine equations. And in fact, again, I want to begin by talking about Diophantine equations. The term Diophantine equation comes from the name Diophantus. He was a Greek mathematician who lived around 200 AD. He was really interested in looking at the integer solutions of equations. So any equation can be seen as a Diophantine equation, but if we want, instead of looking at all the possible solutions, we just want the solutions that are composed of integers. I'll give you some problems that you can reflect on. I'll start with a very practical problem. For example, in how many ways can a debt of, let's say, 65 pesos be paid in 10 peso and 5 peso coins. Of course, 65 is very small. One way of paying it is if we have 6 tenths and 1 5. Or we can have 0 tenths, no tenths, but we can pay it purely in 5 peso coins. So we have 13 coins. And of course, we can of course express this algebraically. Can you think of the equation? Yes, Alvin.
That's 65 is equal to 10x plus 5y.
10x plus 5y, 65. No? So 10x plus 5y is equal to 65. This is an example of a Diophantine equation. So we have coefficients of x, coefficients of y, and a constant term. The question here is that how many integer solutions there are. Of course, we want our x and y to be integers, because x and y are just the number of coins with which we pay the debt. Okay? If we do not require this to be integers, for example, if we allow x and y to be real numbers, then we have infinitely many. This is just the equation of a line, right? Yes. Yeah. So think of the solutions like this. If you imagine the line on the xy plane represented by this equation, the solutions we want are those points that are purely integral in coordinates. All those real number ordered pairs which are integers. So this is one example of a Diophantine equation. I'll give you another Diophantine equation, this time asked by the Greeks. The Greeks, of course, wanted solutions to these equations. Another Diophantine equation. Can a perfect square be the sum of two perfect squares? Think about that question. It should be very familiar to you. Yes, Alvin.
It's just an expression of the Pythagorean theorem, which is c squared is equal to a squared plus b squared.
Yes, this is just the Pythagorean theorem. No? What we want is that can a perfect square be the sum of two other perfect squares? So what this question wants are solutions to the Pythagorean theorem. For example, 5 squared is equal to 3 squared plus 4 squared. So we say that 3, 4, 5 is a solution. I'll ask you another question. My third question. Is there a perfect cube that exceeds a perfect square by 2? Can you think of a perfect cube and a perfect square that are so close apart, their difference is 2? Yes, Joseph?
2 and 4.
2 and 4. Well,
2 is equal to 8.
yeah.
The square of 4 is equal to 16.
Yes. Okay. But when we say exceeds by, we are looking at the difference.
Perfect square and a perfect cube.
Perfect cube and a perfect cube. Yes, Edu.
So, perfect cube is 27 and the perfect square is 25.
Yes, 27 and 25. With this question, what we want are solutions. Y squared is equal to x cubed minus 2. So one possible solution is x is 3, y is 5. Another solution is x is 3, y is negative 5, right? So now we have two solutions. The question, are there other solutions? This is a very old question, but somewhere in the 18th century, it was shown using imaginary numbers that there are no other solutions. In my third lecture, I will talk about Euler. Showed that 3, 5, and 3, -5 are the only solutions.